All right, in this video, we will be going over our shortcut rules for differentiation. All right, so we're going to start with our first rule that we'll probably use the most, called the power rule. It says if n is any number, then ddx of x to the n equals n times x to the n minus 1, provided x to the n minus 1 exists. Okay, so this is useful for monomials, for polynomials that are made with terms that have x to some power. We've got Justice League's going to help us understand these rules today. Green Lantern says bring the exponent out to the front and decrease the power by 1. So what these are is a series of shortcut rules to allow us to take the derivative without having to use the limit definition. Okay, and they will give us new derivative functions. We can use them to find those functions, or we can use them to find the derivative at a point. Okay, so it says the key to using the power rule is to get comfortable using exponent rules to write a function as a power of x. So sometimes, like in example 1a, it'll be a straightforward use of the power rule. So in a, we've got f of x equals x to the 5th power. So the power rule says take that exponent 5, that now becomes the coefficient, and the new exponent is 1 less than that. So 5 minus 1 is 4. So it's saying 5x to the 4th is the derivative of x to the 5th. All right, if you plug in a x value, that'll give you the slope of the tangent line at that point on that original curve. Okay, part B. Sometimes functions don't present themselves as a standard monomial, as a standard x to a power. In some cases, we can rewrite them as x to some power. So for radicals like this one, we've got the cube root of x squared. So we can rewrite any radical and use the index as the denominator of that radical. And so for cube root of x squared, we can rewrite that as x to the 2/3, and then we can use our power rule. So take that 2/3 to the front, that becomes your coefficient, and then we've got to do some subtraction. So we got to be careful about subtracting a whole from a part. All right, 2/3 minus 1 is negative 1/3, and depending on what we're using these for, in the future, we will be okay with negative exponents, but for now, so that we get comfortable with what these derivatives look like, let's get rid of that negative exponent, and you're welcome to rewrite it in radical form. These check marks just show that I'm okay with actually any of these 3 forms for your answer. Okay, part C is similar. We've got x to the 4th in the denominator. However, we can't use the power rule just in the denominator of a fraction. We can't use it just in the numerator of a fraction. We've got to take that whole function, which is 1 over x to the 4th, as a whole. What we can do is we can rewrite it with a negative exponent, right? 1 over x to the 4th is the same thing as x to the negative 4th. So take that negative 4, that's our power. That becomes our new coefficient of our derivative. And be careful with subtraction of those negatives. Negative 4 minus 1 is negative 5. Okay, and again, I'm okay for now, unless the directions say something different, with a negative exponent or with rewriting it with a positive exponent or with a radical. Okay, but be careful. We can't just keep the 1 on the top and do the power rule in the denominator. This is not the same as 1 over, what would that be, 4x cubed. Okay. All right, next rule. The derivative of a constant function. It says if c is any constant value, then ddx of c is 0. So think about our constant functions, horizontal lines. The derivative, let's not get too bogged down in the algebra of these shortcuts. We're still finding derivatives. We're still finding slopes. Slope of a horizontal line is 0. So regardless of what that constant number is, derivative of any constant is 0. So if you're asked to find the derivative of, in this example 2, f of x equals 5, there's no x in there. That's a constant function. The derivative is going to be 0. All right, next rule, the constant multiple for derivatives. All right, if u is a differentiable function of x and c is a constant value, then d dx of cu equals c times du dx. This kind of starts a trend in calculus that we'll see of replacing pieces of functions with u's and v's for whatever reason. But just know that u is a function itself. In this case, it says it's a differentiable function. And we just got some constant in front. So one of them says the derivative of a constant times a function is the constant times the derivative of the function. It essentially says we can factor that constant out to be a coefficient of the whole derivative and then take the derivative of what's left. So in example 3a, we've got 5x to the 7th. So this rule just says, hey, we can factor that 5 out. Okay, I've written it using the notation of our rules here. Factor that 5 out and then use the power rule on x to the 7th like normal. You're going to have a 7 factor to multiply by that 5 because of that power rule. So make sure that you simplify those simple products in your final answer. All right, so we get 35 times x to the 6th power. All right, you guys can do example B, and you can check your work with this here. I've also given another example C, where g of x equals 7x, just for extra practice. Check your work there. Feel free to pause this as much as you want, obviously, as you need to copy this stuff down. Okay, the sum and difference rule. All right, page 2 says if u and v are differentiable functions of x, then wherever u and v are differentiable, d dx of u plus or minus v equals du dx plus or minus dv dx. All right, Aquaman says take the derivative of each one individually and add or subtract them. So this is nice. This is a really handy rule that says, hey, if our function has like multiple terms separated by pluses or minuses, then we can kind of divide and conquer. We can take each of those terms and we can take the derivative of those individually and then put all those back together to get the derivative of the whole. Okay, so example 3a, we'll look at that one together. We've got this 4-term cubic polynomial, and if we want to find the derivative of that, then we can break it down and take the derivative of each of those individual terms, all right, one at a time. All right, this is really handy and one that we'll be using over and over and over again. You don't have to rewrite this out like I did here. I wanted to show that rule in action. Okay, so we can, as we get more and more comfortable with these, especially with this product rule and the constant rule and the coefficient rule, you don't need to write this top term. We can go straight to, hey, take the derivative of this term. What is that? It's 3x squared. All right, take the derivative of the next term. What is that? 2 times 4 is 8. 8 times x to the first power. Boom. What's the derivative of any linear term? It's going to be that coefficient, all right, -2 there. What's the derivative of a constant? Derivative of a constant is 0. You don't need to put that plus 0 on the end of your final answer. All right, so final answer is this guy right here. Oh, no, it's not letting me click. All right, let's see how we're doing over here. Okay, you guys can try B on your own and check your answer here. Be careful. You may have to do a little bit of simplifying before you can apply these rules with the functions that you're given. Okay, they're oftentimes not given to you in a form where you can just jump right into a rule. Okay, so be careful about that first term in B. All right, let's see. Real quick. Example 4, we got a tangent line function. All right, we know that we're going to be asked to find tangent lines going forward. Same type of question we could have been asked last unit, but now we have a shortcut to find the derivative. All right, so plug that 2 into your function to find the y value. All right, your y1 is 25. So right ahead, you can plug that into your x1 and your y1, and then to find that slope, take the derivative of f of x. Plug in 2 when you get that derivative. Okay, that'll give you that 42 slope. And final answer is here.